So as you know, an orbit of zero eccentricity is a circle. An orbit of eccentricity between 0 and 1 is an ellipse. An orbit of eccentricity equal to 1 is a parabola. And an orbit of eccentricity bigger than 1 is a hyperbola. The circle and the ellipse are examples of bound orbits, and the parabola and the hyperbola are examples of unbound orbits. By bound means that the energy is negative, and unbound means that the energy is either zero, in the case of the parabola, or the energy is positive, which is the case of the hyperbola. So let's see how we can get to the geometry of these orbits in the same way that we found the geometry of the ellipse for the bound orbits. So if we start from the definition of the eccentricity, that the eccentricity is the square root of 1 plus twice the energy times the angular momentum square over gm squared. And let's substitute the gm by mu. If we isolate the angular momentum, so we see that at constant angular momentum, increasing the energy increases the eccentricity. If you consider the definition of the energy, which is v squared over 2 minus mu over r, it is a combination of kinetic energy and potential energy. If the energy is negative, it means that the gravitational potential energy is larger than the kinetic energy and the orbit is bound. Now, considering that the energy is negative, then the definition of eccentricity. So if the potential energy is bigger than the kinetic energy, the energy is negative and the orbit is bound. Now, by the definition of the eccentricity, if the energy is negative, since this is 1 plus a negative term, this has to be between 0 and 1. So the orbit is either circular, which is the case of eccentricity equals 0, or an ellipse, which is the case of eccentricity between 0 and 1. So these are the bound orbits. Let's take a look at the unbound orbits. If the energy is exactly equal to 0, that means that the system has just enough energy to reach infinity with 0 velocity. Now in this case, the eccentricity is equal to 1. But what orbit has eccentricity equal to 1? According to the definition of the semi-major axis, if the energy is equal to 0, then the semi-major axis shoots to infinity. According to the equation for the angular momentum, if the eccentricity is equal to 1 and the energy is equal to 0, you have 0 over 0, and then the angular momentum is indefinite. So to identify the geometry of this orbit, let's go back to the equation of the orbit, Kepler's first law. So the equation of the orbit is r is equal to L squared over mu over 1 plus e times cosine of the true anomaly. Let's write that in terms of the semilatus rectum. So r is equal to p over 1 plus e cosine f. And let's now use the fact that the eccentricity is equal to 1, so that the radius vector becomes more compact. It's the semilatus rectum over 1 plus cosine of the true anomaly. Now the semilatus rectum, as the angular momentum is indefinite, but at least we know that it's constant. So let's see some of the special points of this orbit. At perihelion, you have that cosine f is equal to 1 because f is equal to 0. So the radius vector at perihelion, let's call it q, is equal to L squared over 2 mu. Now at aphelion, the true anomaly is equal to pi. So the cosine of f is equal to -1, and the radius vector is infinite. So if the radius vector goes to infinite, then the orbit is not periodic, as we expect for an unbound orbit. So we don't know yet what the orbit is, but let's draw what we know so far. We know that it has a finite perihelion distance. We know that this distance is equal to p over 2, and we know that it opens up to infinity. So let's define the coordinates. Let's set the planet at a random point. The radius vector is connecting the sun to the planet. Let's now define the origin at the perihelion. So this is y, and this distance is x. So the true anomaly goes from perihelion to the radius vector. Let's define this here as the angle beta, where beta is 180 minus the true anomaly, the complement of the true anomaly. So we can write that this distance is a distance q. So the position x of the planet is q plus r cosine beta. Y is equal to r sine beta. And because this length here now is x minus q, then by Pythagoras theorem, r squared is equal to x minus q squared plus y squared. So let's consider the equation for x. Now let's isolate the cosine beta, which is x minus q over r. Now write this in terms of the true anomaly. It's cosine of 180 minus f, which is minus cosine beta. Therefore, the cosine of the true anomaly is equal to minus x minus q over r. So now let's consider the equation for the radius vector with the semilatus rectum and substitute now this expression for the true anomaly. So the radius cuts on both sides, and I have that r is equal to p plus x minus q. Now let's use both of these equations for the radius vector, this one and this one. So if I isolate y and write the radius vector according to the second equation, expand the first square, the x minus q square cuts, and we have the I square is equal to p square plus 2p that multiplies x minus q. Now, if you consider again the definitions of the semilatus rectum, p is equal to a times I minus z squared, and q, the perihelion distance, is a times I minus z. Then if you write the semilatus rectum as a times I plus z times I minus z, you can substitute the q in here. This is equal to q times 1 plus e. Now for eccentricity equal 1, q is equal to p over 2. So if you substitute q equal to p over 2 in here, the p square cuts, and you have y square is equal to 2px. And y square equal to 2px is an equation of a parabola. So if the star is here, this is the perihelion distance q. The semilatus rectum is equal to 2q. Notice that the semilatus rectum depends on the angular momentum. Now, if the angular momentum is 0, so is the semilatus rectum. That means that y is equal to 0 at all points, and the orbit then degenerates into a line. The perihelion distance is also going to be 0. That means that the line crosses the sun. So a parabolic orbit is an orbit of eccentricity equal to 1 and non-zero angular momentum. For 0 angular momentum, the orbit becomes a line and plunges into the sun.